Let's discuss question number 41 from test 1. A pump running at 1000 rpm consumes 1 kilowatt, generates head of 10 meters of water. When it is operated at 2000 rpm, what is the power consumption head generated? So this is straight from centrifugal pumps, and so it is from fluid mechanics. Okay, so pump running. So one of the condition is given. Initially it is running at 1000 rpm, consumes power at 1 kilowatt and generates head of 10 meters. Now I change the speed to 2000 rpm. What happens to power? What happens to head? Well, now something which we need to understand here is our scaling laws for the pumps. Now, how when I change the operating response, or I change basically the dimensions, so then how does all these speeds, power, discharge, how does this change? Scaling laws for pumps. There are three equations which we again derive it from non-dimensional number. So let me just write down those three. Hn square is constant. Okay, this is first. The second is your n root q by h3 power 4 is constant, and your p by qh is constant. Now this can be applied between model and prototype if there are scaling. If there is, like, you're doing an experiment on the model, I want to build on actual prototype, so this can be applied between model and prototype also. Even if the same pump, you just want to study the operating response, like this problem at 1000 rpm, this is what is happening at 2000 rpm, what happens. So all those problems can be done with the help of these. Now it's matter of question now which of these three I have to select in order to get the required. Now we want head and want p, so n and p has to be individually related, n and h has to be individually related. Now let's see n and h. We can use the first equation because diameter is constant, so I can just write h n1 square is h2 n2 square, and from this I can get h2 by h1 is n2 by n1 whole square. So n2 is 2000 and this is 1000 whole square, so this is 2 square, which is 4. So head is 4 times h1, which is 4 into 10, so 40 meters of head. So this is what I get from the equations. Okay, so one of the answer we got. Now we need to relate n and p individually. Now n and p I have here, but I don't have discharge. I need to eliminate discharge. Now how do I eliminate this? So this is constant again, so from this q I can just keep it in here. So from this, q is basically p by h into some constant k1. Okay, now this I'll put this in the second equation. So n root p by h into k1 by h3 by 4, it's some constant k2. This I can write n root p by h is half, so half plus 3 by 4 is your k2. So this becomes n root p by h 5 by 4. So I can just take LCM and I'll get something called, all these constants I'm just removing and writing a big constant. Okay, now again h is there. Now h again is related to n square with the first equation. So h is n root p by h, I can write as n square into some constant. So n square, 5 by 4 into some constant. So all these constants I'm just bringing to the right hand side. So this can be written as n root p by n 5 by 2 is equal to constant. Okay, so now if I just square it on both sides, so n square p by n power 5 is constant whole square, which is another constant, bada constant. Okay, so this will be your p by n cube is constant. So this is basically you have derived an expression combining all these three scaling laws, because always these three are related, which we get from non-dimensional analysis for pumps. So you have to always remember these three, and from this whatever is required you can derive it. So P by n cube is constant, so we can write P by n1 cube is P2 by n2 cube, or P2 by P1 is n2 by n1 whole cube. n2 is 2000, this is 1000 whole cube, it is 8. So P2 is 8 times P1, which is 8 times 1 kilowatt, which is 8 kilowatt. So 8 kilowatt is the new power at 2000 rpm, and power which it will consume and expected to consume, and head is 40 meters. So looking at the options, option is D. Thank you.